Let me discovered a neat new tool on my computer that I didn't know I had, but it's pretty cool. What it allows me to do is write on your document.
Oh, cool.
Yeah, really. I can't wait to practice with it. So I might be a little bit stupid as to how to use my own program, but I think it'll make things better because, for one thing, I don't have to redraw everything.
Yeah.
Now, I'm not sure why they went out of their way to make this more confusing by labeling the x-axis some number of a and the y-axis some number of a, and then apparently in this case a is 10. Okay, so we have an x-axis that has 20 from 0 to 2a, and we have a y-axis that has 10 from 0 to a. Okay. Now, in geometry, we learn how to figure out the areas of things by if they're straight lines. In other words, if you have objects that are all surrounded by straight lines, it's relatively easy to figure out the area. Or if you have certain curved lines like circles, you can figure out the areas of circles. But in general, when you have curved lines that are not circles, then all of a sudden we don't have any geometry for figuring out the area under that curve. So what they did for thousands of years was to break it up into rectangles. Put a rectangle there, rectangle there, rectangle there, figure out the area of each rectangle, add it all up.
Oh, wow.
That's how they did it until Newton came along and figured out the way to do it exactly. Now, they still teach calculus by starting off showing you pretty much how they did it for thousands of years. And that's what this problem is all about. Okay? Part A says use 5 rectangles to find the lower estimate and an upper estimate for the area under this curve from 0 to 20, which in this case is from 0 to 2a. Okay. Now, maybe I can get away without using my other drawing tablet. One way to do it would be if I started with rectangles whose left upper corner intersected with the graph, like that. Okay? They want 5 rectangles. Well, how many rectangles, what's the width of each rectangle got to be if they want 5 rectangles between 0 and 20?
4.
Okay, so that width is 4. Okay, now I'm going to put another rectangle in there starting with the upper left hand corner that's also 4 units wide, and I'm going to do that strategy. Notice my third rectangle starts in the middle of a grid, but still end up with a rectangle. And my fourth rectangle starts there, goes to there, and finally my 5th rectangle and last one is that. Well, it's not that hard to figure out the area of these rectangles. I know that they're each 4 units wide. This first rectangle is 2 units tall. Second rectangle is 6 units tall. The third rectangle is about 9 units, and so forth. Okay? Now, notice what is happening here is that I am underestimating the true area under that curve, right? I mean, look at all this area here that's not being counted. All of those areas right there are not being counted in my estimate, and so I'm clearly getting hopefully an underestimate. Okay? And that's what they're calling a lower estimate. Well, traditionally, I have some issues with the way they're teaching it. I get lower and upper, but sometimes left hand and right hand is what is needed to really understand this stuff. Okay? Now, let's see. If you need a lower estimate, let's add it all up. What's the area of the first rectangle? We'll even call it number 1. It's 4 units wide, 2 units tall. Its area is 8. What's the area of rectangle 2?
So it's 2 and 6, 12?
It's 4 and 6. In other words, it's 4 between there and there, and it's 6 units tall. So 4 times 6 is 24. About number 3. And notice this says estimate. So there's not going to be a right answer or a wrong answer as long as we're close. Okay. So number 3 is also 4 units wide. How tall is it? 1, 2, 3, 4. About 9. So 4 times 9 is 36. Rectangle number 4 is 4 times 11, 44. And finally, rectangle number 5 is 4 times, that's 10, 12, 13. 4 times 13 is 52. Okay? Add all those up and we get 32, 68, 112, 164. That's the area under that curve, but we know that that's a lower estimate. It's not the true area. The true area under that curve, we can tell, is going to be bigger than that. If you want to put in a number, go ahead and put in 164 for that first A lower estimate. Just so we can go on and I can erase some of this stuff.
All right, yes, it's correct.
Got it? Okay. Now, hold on a second. Erase all ink. Wow, okay. I'll know better than to do that in the future, although it's okay. Now, that method that gave me a lower estimate was based on putting the upper left-hand corner of the rectangle on the curve, right? In other words, my first spot was there, and my rectangle had to be 4 units long, so that's how I drew the rectangle. Now, that's called left-hand, and there's another method called right-handed, where I put the upper right-hand corner of the rectangle on the curve, and I draw my rectangles like this. Notice what I'm doing. Be very careful, or pay very close attention to how I'm figuring out the right upper corner of this rectangle. It's right there. In other words, it's on the curve. This one's going to be right there. This one's going to be right there. Now, notice that when I use this method, which is called rram, which means right rectangular approximation method, I overestimate the area. I got all this area in here that is outside the curve, but it's going to be included in my rectangles. So again, let's go through and do the upper estimate. In other words, rectangle 1's area is what?
So it's still
4 units wide. How tall is it?
And now it's 3.
Each unit is 2.
Oh, 2.
Each grid mark on both the x-axis and the y-axis are 2 units.
Okay, so it's 6.
Okay, so that's 4 by 6. How about the second one? That's
8.
No, that's 8. Or, excuse me, that's 9. That's not on a grid.
Right, it's not.
It's halfway up. Okay, so that's 4 times 9. Third one is going to be 4 times 11. Fourth one is going to be 4 times 13. These numbers look familiar. They should. We just went through these, only we're shifting 1 unit or 4 units to the right. And this last one goes to 10, 12, 14, 15. 4 times 15 is 60. Add all of those up, we get 60, 104, 156, 216. That's the upper estimate of the area under that blue curve. Go ahead and put that in for your upper estimate answer.
All right.
Now, here's the thing. The reason they do not teach it as left ram and right ram anymore is because left ram doesn't always underestimate it and right ram doesn't always overestimate it. It depends on whether the curve is increasing or decreasing. Okay, for example, if I had a curve that was decreasing like that, and I use left ram, I overestimate it. Right?
Yeah.
Whereas if I use right ram, I'm underestimating it. So which one is over and which one is under changes depending on whether your curve is increasing or decreasing. And that's why I kind of like the terminology left ram, right ram, and mid ram. Mid-ram would be where I would take the middle point of the rectangle, draw it like that. And notice, that's the best one yet, right? That's got a little bit of space that's outside the curve, and it's missing a little bit of space that's still under the curve. Well, that's our best approximation yet. But that's not their point here. They're trying to illustrate a point. So we answered A. Now they say do the same exact thing for B, only use 10 rectangles. Well, 10 rectangles means each one of them is only going to be 2 units wide. Watch carefully how I'm drawing these. I always start the upper left-hand corner on the curve and draw the rectangle exactly across. Okay. Now, what they're going to illustrate here is the fact that if you use more rectangles, you get a more accurate answer. In other words, we got a certain approximation when we used only 5 rectangles, but you can kind of see by this drawing that this is going to be a better approximation than when we only used 5 rectangles, right?
Mm-hmm.
It just is. The more rectangles there are in this space, then the closer you are to the exact amount. Okay? And if you want a lower estimate on this, I'm not sure at this point how much time we should be spending on adding up numbers.
Probably not that much, I think.
Well, I would think you'd be better served if we went on and explained the concepts and how why we're doing this. Okay.
Agreed.
And the point of this problem, by having you do 5 rectangles and having you do 10 rectangles, is they're going to illustrate to you that the 10 rectangles is a more accurate estimate. The distance between the lower and the upper is going to be less. The range between those two is not going to be as big as it was using 5 rectangles.
Mm-hmm.
Okay. Now, if I were to do right rectangles, right ram, that's the way I would do it. Notice I begin, I'm very, very exact with where I begin. I'm beginning the upper right-hand corner of the rectangle where it intersects the curve. And I make my rectangle. Okay? And you can see once again that using right rectangular is going to overestimate it. This particular case, because it's an increasing function. Now, not to get ahead of ourselves, but somebody came up and realized that, wow, what if I use a trapezoid instead of a rectangle? That's going to estimate it really good, right? So there's also the trapezoidal method, which they're probably going to teach you if they haven't talked about yet. But all of these methods were the ones that were used for thousands of years whenever mathematicians had to figure out the area under a curve. And the more rectangles they put in there, the more accurate their answer was. So you had people drawing hundreds of rectangles under curves, or better yet, trapezoids, just to improve upon the accuracy of the area under that curve. But we're going to do the same thing in B as we did in A. We're going to use left hand and right hand. Now, let me see whether I can pull up. Yeah, okay. Here we go. Is this the next problem? Yeah.
Yes.
Okay. Let me sharpen that up a little bit. That focus was not the best.
Oh, that's still the first one. Oh, yeah, there we go.
Yeah, no, notice how it's a little blurry?
Yeah, I think it's because I had to zoom. I zoomed out. It's because of the screenshot I took.
Okay. Consider the following. Use 6 rectangles, but they will not let up on these rectangles, huh? Use 6 rectangles to find estimates of each type for the area under the curve. Okay. Again, let's spend a little bit of time on this, but not a lot of time. Okay. Now, the area under the curve, let's see, each one of these is 4 units, so that's 1, 2, 3, 16. That should be labeled 48. Oh, how cool is this? And I don't even have to write in anybody's book. So notice this is a decreasing curve.
Mm-hmm.
We're going to use 6 rectangles. How wide is each rectangle going to be?
Is it 8?
Which is right there. Okay. So if I put a rectangle every 8 units, I'm going to end up with 6 rectangles.
Mm-hmm.
Now, let's examine both types, the left ram and the right ram. I don't know how they can even teach this without that concept, because you don't know. In other words, I guess you could assume that that's going to overestimate it, that's going to underestimate it. And that's kind of what they're thinking, I guess. I don't know, but I think it's worth understanding left ram and right ram, because it gives you a starting point. In other words, if I want to know how to draw my first rectangle, well, I know what its width is, but where do I begin it up top? Well, if I'm using left ram, then I pick its upper left corner and match it to the function and draw a rectangle. Second rectangle, I do the same thing. There's the upper left corner. Same thing with the third. And the fourth. And the fifth. Notice I'm not always starting on the grid. I'm starting wherever the upper left-hand corner intersects with the curve.
Mm-hmm.
Now here I used left ram, but we're overestimating by a lot.
Uh-huh.
And right ram, if I were to put right ram in there in red, red's not a good color to use, let's use green. If I were to put right ram in there, that's where my first rectangle would go. See why? Because I'm putting the upper right-hand corner of the rectangle on the function. Well, that's that spot, or that spot, or that spot, or this spot, and finally, that rectangle. So if I use right ram, I'm severely underestimating it with this decreasing function. And I guess the exercise here is to find estimates of each type for the area under the curve. Hold on. What's the rest of that say? From x equals 0 to 48. Now when they say find estimates of each type, I presume they mean left ram and right ram. Those 2 types only.
Yeah.
Okay. All right, well I just did that. Okay. In other words, I showed you the left ram, which in this case overestimated it, and I showed you the right ram, which in this case underestimates it. Sample points are left endpoints. Okay, so what this A sub I means is that they're using left ram. In other words, where I start is the left endpoint of the rectangle, the left upper endpoint. So that would be the same as what I'm calling left ram. Sample points are right endpoints. That's what I'm calling right ram. And sample points are midpoints. That's mid ram. Okay? Let's have a, hold on a second. Gotta figure out how to, let me just real carefully show you how mid ram would look like. In other words, I'm going to take my rectangle, and instead of centering it at the left corner or the right corner, I'm going to center it right in the middle, right there, such that my first rectangle looks like that.
Oh, okay.
Okay. The second one, there's the middle. So the second rectangle looks like that. The more curvature in the line, the more difference it seems to make. But it's pretty easy to figure out that mid-ram is the best of all possible worlds, right? Makes you even wonder why the heck they even teach left ram and right ram. Mid-ram is what you would go with. But like I said, trapezoids are even better. If I was using trapezoids, I would end up with a line like that and a line like that, straight lines. So they're not perfect, but they're certainly better than rectangles.
Mm-hmm.
All right, so that takes care of A. And what they're asking in B is, when I use left endpoints, am I overestimating or underestimating? Well, on this particular curve, you're overestimating. So B is overestimating. And when I use the right endpoints, as I showed, I'm underestimating. Which of the numbers gives the best estimate? Well, like I said, the mid-ram appears to, and usually does, almost always gives the best estimate is mid-ram. So you'd want to answer D on that.
Okay. So for the left endpoint, sorry, did you say, what exactly is the answer? Is it 0 and then the right is 8? Or?
No? Okay, yeah, let's talk about that. In other words, you want the answer, the sample points,
yeah,
points, so you want to know what L6 is.
Yeah.
It's a left endpoint. And what that means is that I'm going to start right there. The upper left-hand corner of my rectangle has to start at 0 and
0.
Intersecting wherever the curve is.
Okay.
It's where it's at, which is at 36.
Okay.
And now I just draw a rectangle, straight across. Whoops.
Okay.
Straight across and 8 units wide.
Okay.
Now for my second rectangle, I start right there. That's using left endpoints. And you can see immediately that the left-hand one overestimates the area. It's got all this extra space up above the curve. So in this curve, left-hand endpoints are going to overestimate, right-hand endpoints are going to underestimate. If I was doing right-hand endpoints, I would start my first rectangle there. That would be my first rectangle.
Excuse me.
Notice that underestimates it. There's a lot of area between the top of that rectangle and the pink curve. So I'm going to be underestimating it the whole way down.
Okay.
But this is the right-hand endpoint. And you can call it however, I'm shocked that they don't use lram, mram, and right ram anymore. But that's okay. It's not the first time I've encountered that. I've seen it before, and I've always wondered about how they get across the point. You ready to move to the next one?
Yes.
Trying. Okay. Now here they give us the function. They don't just say it's some function. They actually tell us what it is. And that's going to be very useful because we're going to be able to calculate exactly. Okay? So we want the area under this curve from 0 to 4 using 4 approximating rectangles and right-hand endpoints. Can you see why this picture here is right-hand endpoints?
Yes.
First rectangle started there. On the other picture, they're using left-hand endpoints. No, they're not. They're using I don't even know what they're using on the other picture. It doesn't look to be consistent. In other words, they're clearly using something different. It looks like left-hand endpoints on this one, right there, but then they don't use a left-hand endpoint there. Otherwise, that rectangle would look like that, and this one would look like this. So I'm not sure what the right one is doing yet, but I don't need to be sure. We'll get to that when we get to the question. All right, so let me just scroll over and make sure I'm reading all of the directions. Round your answers to 4 decimal places. So R4 is the area of the blue, correct?
Yes.
Okay. I can write over here on the right side for this one. Tell me the area. In fact, I can write right here. I'm going to write the area inside the rectangle. What is it?
Okay. So it's 1 times, so 20.
Okay. That one's 20. What's the next one?
So it's 228 times 2, correct?
Not times 2. The width of that rectangle is still 1.
Oh, right, okay. So 28.
The area of the rectangle is the width times the height.
Right. And then 34, and then 40.
Notice that we're kind of guessing a little bit, right? Because we're not able to read the grid perfectly. Well, let's go back and figure out what that value is, so I don't have to guess. When x is 1, what is f of x?
20.
So we were perfect there. That is 20.
Okay.
But here in the second one, instead of guessing, let's plug in x of 2. And what is f of x? when I plug in x of 2?
It's still 20.
It's 20 root 2. What is that in your calculator? Do 20 root 2. Do you have your calculator in front of you?
Yeah.
Okay. Root 2 is like 1.41, so 20 times it is going to be a little bit more than 28.
Yeah, it's 28.3.
Notice how we're doing these now. We're not reading the values off of the chart. We're plugging in the x coordinate into the function. So what is this value? What is that height?
Let's see, like 34.6.
So that's 20 root 3?
Yes.
Remember, it's root 3 now. It's not root 2. In other words, the x value is 3. So f of x is 20 times root 3. What was that number again?
34.6.
And finally, plug in 4 for x into the function. And what's the y value?
40.
Okay. So that's 40 times 1. So we got that one right. But notice the other two, we sure didn't want to read that from the graph. We were significantly off. You want to get that value from plugging into the function. That's a very key part of the process, is that you don't really care what the height is. What the height is, let me write this like this. This is f of 1. This is f of 2. And you know what I mean by that? In other words, to calculate what the height of each of those rectangles is, we use f of 1, f of 2, f of 3, and f of 4. We don't try to read it off the y-axis. We just plug it in. Well, f of 1 was 20. F of 2 was 28.3, f of 3 was 34.6, and f of 4 was 40. So add those four numbers up and put it in for R4, and you've got a right estimate, a right endpoint estimate.
Okay.
I guess when they use L and R, they're basically doing the same thing that I'm doing or talking about when I talk about left ram and right ram and mid ram. Only they're not using the ram. RAM just stands for Rectangular Approximation Method. So LRAM is left-handed Rectangular Approximation Method. Okay. Now, this second graph over here that they've put these rectangles in. Ah, I see what they've done. This point is left-handed, right?
Yeah.
This point is mid-ram.
Oh.
And this point is right ram.
Right. Oh.
So they're essentially saying to you, I can use combinations of these things, and it's not going to matter in the long run. And that's the truth, actually. In other words, in the long run, you are going to put an infinite number of rectangles below that curve. You're going to put so many rectangles that they're going to look like this. Just hundreds of them. Okay? And when you increase the number of rectangles, then it matters less and less whether you're using left hand, right hand, or midpoint. As the number of rectangles goes to infinity, or I can say as the width of each rectangle goes to 0, then it does not matter which method I use, left hand, mid ram, right ram. And that's what this is trying to show you by using a combination of all three.
Okay.
But it still is, let's just talk about this again. That point right there is f of what? On the y-axis.
It's still f of 1.
What's this point?
F of 2.5.
Good. And what's this point?
F of 4.
Yeah, and by that I mean that's its value. That's f of 1, that's f of 2.5, that's f of 4.
Right.
Or f of 2.5 was there. Okay. On. Oh, I kind of get it. Using 4 approximating rectangles and right-hand endpoints. Well, this one they use nothing but left hand on the left. And on the right they use nothing but what? What is that on the right that they're using?
A middle.
Midpoint, right. That looks like a pretty good estimate, right? I mean, you got extra space there, but you got under approximation there, over, under, and they appear to balance one another out. So that midpoint looks to be a really good approximation. But if I wanted to make it better, I would just add the number, increase the number of rectangles. I'd put 8 rectangles instead of 4. And to make it better yet, I'd put 16 in there. And to make it really good, I would put 1,000 rectangles.
Yeah.
Then I would have almost the accurate point. The ultimate end in integral calculus is you integrate the function and you get the exact value without having to do all of this or without having to do all this rectangular stuff. I'm not sure which of these questions goes with which curve, but I think you can take it from there. Let's just see what they're doing on this curve here. What is this curve on the left?
Right.
Okay. And the curve on the right
is middle.
And what is this point right there on the y-axis?
0.5.
F of 0.5.
Right.
Well, and to figure out what f of 0.5 is, I'd plug it in. In other words, f of 0.5 is 20 times the square root of 1/2. That's what f of 0.5 is. Notice that it appears to be at about 14, but it's not going to be 14. It's going to be some decimal number. This point here, I don't know if you can see, this point that I'm pointing at right there, what's that?
F of 1.5.
Okay. I think you're getting it. I think you're understanding what they're asking about here. Boy, they sure give you lots of graphs that are basically doing the same thing. This one's a little different. Notice that the first rectangle is what?
Left.
The middle one is?
Middle, and then right.
The right one is?
Right.
Okay. And again, that's f of 1. That is f of 2.5, and that is f of 4. Okay. And on this one over here, they're using left endpoints.
Right.
Now, let's just clarify something here. Technically, there's another rectangle right there, right?
Mm-hmm.
In other words, it looks like they've arbitrarily skipped that one. But they didn't. It just had 0 height. But they should have done it for clarification's sake. In other words, this first rectangle that goes in this box starts right there. It's not a rectangle, it's just a straight line. That's why you don't see it. But that is still left-handed approximation method. This one that is on the right side here.
Right, that makes sense.
So if your curve goes all the way down to the origin and you're doing left-handed rectangles, you're not going to see a rectangle in that first spot.
Mm-hmm.
If the curve doesn't go all the way down to the origin, in other words, say the curve went like this, well then your first rectangle would be there. Second rectangle would be there, and so forth and so on. Okay, let's go down further. Yeah, is your estimate an underestimate or overestimate? I think you're good on that, aren't you?
Yeah.
Going through each of these problems, it's hard.
Yeah.
It's hard for me to figure out which question goes with which graph. Maybe because I have it blown up too much. I don't know.
Yeah, I'll be better about that next time.
Okay. No, I can go down or up as needed. I generally like to have it as large as possible so that you can see it on your end. All right. You just sent me one page, right?
Yep, that's it.
Okay. Let me think if there's anything else I can add here. Let me think for a second. The next thing they're going to teach you is the trapezoidal method. Okay? If I were to do a trapezoid here, well, there's my starting point. There's my ending point. I connect it with a straight line. I actually get a triangle there. But then if I continue that process, notice that each one is a trapezoid. A triangle is actually a trapezoid of sorts. And I'm connecting these with a straight line. It's following the curve awfully well. And so it's looking like I'm connecting them with a curved line. But notice how much better that is than probably even midpoint. Well, how do I figure out the area of these trapezoids? Well, go back to your geometry. The area of a trapezoid is B1 plus B2 divided by 2. So if I want this area of this trapezoid, that is f of 1, that is f of 2, and that you kind of have to turn it on its side. That's B1, that's B2. You see?
Yeah.
In other words, we're looking, traditionally when you look at trapezoids, you look at trapezoids that are like this. Okay, where that's B1 and that's B2. Well, if I turn that on vertical end like that, well now this is B1 and this is B2. And notice that B1 is f of 2, B2, or excuse me, B1 is f of Yeah, B2 is f of 1 and B1 is f of 2. And it doesn't matter if you mix them up. You're adding them together and dividing by 2 is how you're finding the area of this trapezoid. And the height of the trapezoid is 1. In other words, it's the thickness. It's the distance between that right there. That's the height of each trapezoid. So we're going to add up all of these trapezoids, and we're going to be able to do it because we know the base. We know B1 and B2 for each trapezoid. Just like we knew the height of each rectangle was something called either f of 1 or f of 2 or f of 2.5. In other words, you get your dimensions not by getting a number off the y-axis. You get it by substituting this thing into the function. That's how I know what B1 and B2 are. Is f of 1 is 20, f of 2 is 20 root 2. But that method is coming for you right after left ram, mid ram, and right ram. In fact, I wouldn't be surprised if you get that tomorrow or the next day. And then finally, just a last method that somebody came up with was Simpsons Method. And what Simpsons Method is instead of putting trapezoids in there, you put a trapezoid with a parabola-shaped top. Like that. In other words, it's still a trapezoid, only the top surface is not a straight line anymore. It follows the equation of a quadratic, a parabola. And you can kind of see that method might be the nuts. Because if I put the correct parabola in there, it follows the curve almost perfectly. And that's called Simpsons Method. And most of your calculator algorithms that figure out areas under curve use Simpsons Method. In other words, almost none of them give you an exact number. The only way to get an exact number is you integrate the function from 0 to 4. That will give you the exact area under the curve. But if you're using one of these approximation methods, and that's all a calculator can use is an approximation method. It doesn't know how to do calculus. It doesn't know how to integrate a function. But it can use Simpson's rule or the trapezoidal method to come up with an area that is extremely accurate. And so they may do Simpson's method also in addition to the trapezoidal method, but I'd be extremely surprised if they didn't hit you with the trapezoidal method very next class.
All right.
Morgan, you have any final questions about anything that you're not clear of?
I don't think for now. I just needed to get like a good basis of it before I did everything else.
Not real clear how area under the curve is the inverse of slope of the tangent line. That is really difficult to explain, but it's true. Just as square root of x is the inverse of x squared. Integration is the inverse of differentiation. And,
okay.
We'll leave it at that for now.
Okay.
But both of them have huge applications, both integration and differentiation, in terms of real-life problems. All right.
All right.
I am going to let you go. And, oh, you know what? I wasn't looking at the correct time.
Oh, no, that's fine.
Well, no, when I use that drawing tool, it freezes the picture of my screen, so it freezes the time. And I kept seeing
Oh, really?
47 on there, and I was talking for minutes and minutes, and it wasn't changing.
That's
I
funny.
didn't realize what's going on. So, okay. I'll let you go, and I'll talk to you next time.
Okay. Bye-bye.